Hi everyone. In the previous three lectures, we started our discussion on instrumentation amplifiers. We arrived at a final instrumentation amplifier architecture, which is very commonly used in most of the commercial instrumentation amplifier chips. We discussed that some of the most important properties of instrumentation amplifier is high input impedance, and the most defining characteristic of an instrumentation amplifier is its instrumentation amplifier is just any other differential amplifier. But what distinguishes it is the very high CMRR and preferably programmable gain. And like any differential circuit, since we need good CMRR, it should have a differential symmetry. One common application of instrumentation amplifier is that it has to amplify a differential signal which might be coming from some sensor. It can be a biosensor, or it's commonly used in medical instrumentation applications. So it can be reading a weak differential signal. It has to amplify it to a certain voltage levels, which can then be handled by an ADC. And why do we do that? Because since 1980s, with the advent of digital signal processing, most of the signal processing is done in the digital domain. So therefore, you have to quickly convert your signal of interest, which can be any of these signals from the sensors, to digital signals. Now, before you convert it, this instrumentation amplifier is commonly used as a low noise preamplifier. Okay, it serves as a preamplifier for these weak differential signals from sensors. This signal has to be now then sampled by an ADC. Okay, the moment ADC comes into the picture, so if you are let's say a circuit designer or a system designer who's going to pick an instrumentation amplifier from different vendors, different companies will have TI, ADI, different companies manufacture these instrumentation amplifier chips. And you will have to, when you have to pick the right chip, you will have to you have to keep many other factors in mind. For example, let's say your ADC is a very high resolution ADC, which means its number of bits is really high. Assume it's 20 bits or higher. So in that case, we compute something called as SQNR. SQNR of an ADC is given by 6n plus 1.76. Again, this is a standard result, how to derive signal to quantization noise ratio of an ADC. You can see most of the textbooks will contain, or you can find this on the internet as well. Okay, I'll quote the final result. I'm going to use this result directly. This gives you an idea about what is the SNR of the ADC. Okay, and usually for very high resolution ADCs resolutions in the order of 20 bits and higher, the input referred noise of the ADC will be very low. Okay, this is the noise due to the ADC itself. The sampling circuits, the quantizing circuits in the ADC, they will all add thermal noise. So when you input refer it, that should be really, really low. Okay, if you want to achieve SNRs in the order of 122 decibels, the thermal noise of the ADC itself can end up limiting your performance. Okay, so normally these high resolution ADCs will have very low input referred noise. Now, if I'm adding an instrumentation amplifier in between the sensor and the ADC, the noise added by the instrumentation amplifier also should be very low. Okay, so when you're picking an instrumentation amplifier from one of the from the available vendors, you have to look for its noise specification. You also have to look for its offset specifications. So generally most ADCs will have what we call as a full scale input, that is a minimum and a maximum voltage. Okay, therefore it'll resolve, or it'll convert an analog voltage signal to a digital input signal, to a digital output signal, provided the analog voltage is within a certain range. So that's normally called as the full scale. The full scale is the range of the ADC's input. So normally, if you know the sensor's input signal voltage levels multiplied by the gain of the instrumentation amplifier will give you should normally be within this Vmax and Vmin ranges. Okay, if Vi max and Vi min are the minimum and maximum voltages of the input signal, that multiplied by G should be lower than Vmax and Vmin. Okay, now in the presence of offsets, if you have offsets in the instrumentation amplifiers, offsets we saw, if you recall from our initial discussions on offsets, they will also get amplified, right? Instrumentation amplifier is just the first stage of an instrumentation amplifier is just a non-inverting amplifier, and second stage is also like a subtractor with a gain. So both these stages can amplify offsets. Okay, if the gain is very high, if the gain of the instrumentation amplifier, let's say, is in the order of 1000 or more, then these offsets can also get amplified significantly. So in those cases, you will have to pick an instrumentation amplifier where your input offset is really low. Okay, so that's where these offsets come into picture. And also the next other very important specification is bandwidth, the frequency response of instrumentation amplifier. I'll talk about the frequency response of instrumentation amplifier in the next lecture, but the bandwidth of the instrumentation amplifier also matters, right? Let's say your input signal changes suddenly, and your instrumentation amplifier should be able to reflect that change at the output. Okay, so it should not only amplify the signal, but it should amplify it fast. Okay, if the bandwidth, the 3 dB bandwidth of your instrumentation amplifier is very low, then it won't respond to sudden changes in the input. So bandwidth also comes into the picture, and so it has to, your output, if let's say the input changes suddenly, the output has to settle, which means the output is reacting to changes in the input. It has to settle quickly to those changes. If let's say the input signal changes by a small amount, like a sudden step change from 0 to delta V, the output is going to undergo some settling. Okay, it will settle to the final value, delta V times the gain is what it will settle to. That should settle within a few time constants. Okay, so that the ADC, when it is sampling, it samples the changes as well. So bandwidth matters as well. If your ADC is depending on the ADC sampling frequency, how frequently the ADC is going to sample the output, its input, your instrumentation amplifier's bandwidth should be chosen appropriately. Okay, so these are the other things that to keep in mind when you are picking an instrumentation amplifier. I didn't speak about offsets, bandwidths and all that, because the same rules apply for, these are the things you will have to worry about for any op-amp based amplifier, whether it's non-inverting or inverting amplifiers. You will have to worry about those things even there as well. So all the analysis that we did for offsets, for single-ended non-inverting and inverting amplifiers and buffers, all that will hold true here as well. So that's why I didn't discuss this separately. What I will discuss in the next lectures is CMRR, because CMRR is a very important specification. How do you achieve such high CMRRs? Okay, everything in the differential amplifier, in the instrumentation amplifier will matter. So we'll see what are the different other factors which will impact CMRR and how to design for it. And also we will discuss frequency response. Okay, that I haven't discussed so far. I'll talk about it in good detail. So now you guys know what an instrumentation amplifier is. It is a standalone chip. Many analog companies, analog giants, manufacture those chips. They are used in medical instrumentation applications. They are very low noise differential signal amplifiers, okay, with very high CMRR. So I'll show some two data sheets for two instrumentation amplifiers. The first one here is IN849. This is again a instrumentation amplifier chip from Texas Instruments. Okay, so you can see again this is a very low noise instrumentation amplifier which is used in so you can use it in driving high resolution ADCs. Okay, so again they'll normally give you the applications where it can be used, and so I've told you guys, I think some of them, ECG is like a medical application which is mentioned here, and microphones preamplifiers in speech, so that's also another application. It's a very low noise differential amplifier. It can be used there as well. And you guys can see here, all the offsets and input bias current. So now you know how to read all these specifications, right? Since we discussed all these things for general op-amp based circuits, the same hold true here as well. The interesting thing here you can see here is that they have specifically mentioned the common mode rejection ratio. Okay, and they said it's at least minimum for, say, whatever gain settings you choose, your CMRR will be, CMRR is usually dependent on the gain settings as well, but CMRR is very important when your so when your gain is very high, CMRR is again a very important specification. And that the minimum value of CMRR here is given to be 120 decibels for this. Again, this is an 8-pin chip. I'll again show you guys a list of different chips available from TI. Okay, so here if you guys can recall, this is our instrumentation amplifier that we have been discussing so far. You can recognize this, and there is one external resistor. Okay, the gain of the stage, we have already analyzed this before, and you can see here it's given that the gain can be programmable from 1 to 10,000. Okay, so the feedback resistor is 3 here. The second stage is fixed, you can't program its gain, and the second stage gain is just unity. The feedback and the input resistors are 5 and 5 kilo ohms, so that stage gain is just 1. The first stage gain will be 1 plus 2 RF by R. That is where you do all the programming for the gain. This can go from 1 to 10,000. That depends on how you choose your values of R. So if the feedback resistor is 3 kilo ohms, if I choose my R to be much greater than 3 kilo ohms, then I get a gain close to 1. Okay, if I choose my R to be 3 ohms, then you will get a gain of 1000. Okay, so see guys, the choice of the resistor, the choice of this gain for the first stage will also impact these 3 dB bandwidth of this instrumentation amplifier. So I'll talk about that when we talk about frequency response in great detail. So I'm just asking you to keep that point in your mind. Now there are other flavors of instrumentation amplifiers. So this one is another instrumentation amplifier from TI itself. Now here if you see, the gain is fixed. So the resistor is not external. This is again an 8-pin chip. So this is a very expensive instrumentation amplifier. So none of the resistors, all the resistors are integrated resistors. Okay, so remember, these are all integrated resistors. They are manufactured within a single chip, and they are well designed for accuracy. They are all very well designed. They were well matched on the chip itself. So their CMRR by default will be very, very good. And you can see here, the minimum CMRR is 132 decibels, which is higher than what we saw in the previous example. Okay, so this is a very high CMRR. Okay, so and so therefore again this chip is now naturally priced higher. It's priced, I think, 2-3 times higher than the chip, the price of the previous chip. Okay, so again, like anytime we talk about op-amp circuits, they'll also mention bandwidth and slew rate. See, at this point guys, since we have already discussed so many non-idealities of op-amps, you should be able to read all this data. Okay, fixed gain of 2000, that's just a gain which is dependent on ratio of resistors. Ultra low noise, again this is input referred voltage noise, and these are all the offset voltages and offset voltage drifts and input bias currents. So they depend on the architecture that you choose. So yeah, so this chip is supposedly a very low offset voltage chip, so therefore naturally it costs higher. Okay, so anytime if you see any chip costs higher, either the fabrication cost is higher or the design effort is very high, right? You will have to pay for more man hours. So either higher design effort, fabrication cost is higher, okay, or functionalities are more. The chip is offering you a lot more functionalities, then that will also cost more. So cost will be determined by many factors. Some of the important factors being this, design. If the design effort is high, then it will also cost more. And of course, higher design effort usually translates to better specifications. Okay, higher CMRR, low noise, all that costs more. So yeah, so now I'll just quickly show you guys a data sheet of I think yeah. So here if you see, this is what is shown here is a range of instrumentation amplifier which is available from TI. So you can see here, I mean it lists all the input offset voltages, the gains, the programmable gains and all that, and also it gives you the salient features, what are the main important features, and I'll show you the pin counts. So if you guys can see here, this column here talks about the pin counts. So you can see some chips come with 8 or 10 pins or 16 pins. So the pin counts, the number of pins will dictate your footprint of the chip. Smaller number of pins means the chip will be of smaller size. It also depends on packaging. But yeah, so this is something to keep in mind. And other important thing here is that bandwidth can be mentioned, so that dictates, that will tell you the speed with which the amplifiers will respond. So the ones I'm highlighting in blue, so that's the bandwidth of your uh, you know op amp. And the third and the most important thing here is the CMRR. You guys can see here CMRR's values vary from 80 decibels to 132 decibels. There is 136 decibels here. So these are all 140 decibels here. Okay, so naturally they would also mention the cost per chip. Okay, so yeah, so these cost per chips are also mentioned here. So let me show you this table here. So this one is actually cost per chip, and the quantity, usually if you purchase in bulk, the cost per chip will be lower. Okay, otherwise if you purchase a single unit, it will be higher. Okay, so this is for 1000 units. If you purchase, you get it in the order of few dollars. So again, cost varies from few dollars to few cents depending on what you're looking for. A very low noise, very low drift, a very low offsets instrumentation amplifiers with great CMRR obviously will cost you more. Okay, so few dollars. I think there was a $6 chip which I saw here. Yeah, so this one again comes with a great a very good CMRR and a very low noise levels and input offsets. Okay, so therefore it is priced higher, and its bandwidth is also very high. That's another reason for its increased cost. Okay, so yeah, so this is how you read the data sheet for a instrumentation amplifier. In the next lectures, I'll just discuss what we have left out so far. Because CMRR is a very important specification for the instrumentation amplifiers, I wanted to spend a little more time, which I felt because I didn't see many books discussing, or I've not seen even in application notes that this is being discussed. So I thought I'll spend a lecture or two talking about it. Thank you.